Hi, in this lecture we will be talking about a very important machine learning concept, what you call model regularization. To do that, we have to learn about a new model which we call polynomial regression. If you recall, we have been talking so far about the linear regression model. We need to first learn polynomial regression, which will allow us to learn the concept of model regularization. First, I have shown here a few data points, and can you connect to any functions in your knowledge that follows these data points? Yeah, I think you figured this out, that this is the sine wave that generated these data sets. As usual, our job as a machine learning practitioner is to learn this function from data. And the only tool we have in our toolbox is the linear line, and whatever way you try, you won't be able to fit this function because this is non-linear in pattern. So we have to bring some non-linearity to fit this function. And what knowledge we have so far from our school and college maths? Yes, we are aware of few functions, for example, a quadratic function or a cubic function. So let's look at the formats. So this is the famous linear function, and this is the quadratic function, and this is a cubic function. So if you follow the pattern, so we are actually moving towards more non-linearity if we add more terms to our function, right? So this is, in general, we call polynomial regression. So all the theories that we have discussed so far, these apply to polynomial regression as well, because here only we are adding more and more higher terms to our function. So what I mean by that, if you were able to fit a linear function, you will apply the same to fit a polynomial function, okay? So we are trying to fit this sine wave function, and the first try we have is m equal to 0, meaning that we have only bias, okay? So m represents the degree of polynomial. So here the degree is 0, that means we have only bias term. M equal to 1, meaning that we just added x, a linear function, and then this is with m3, that means this is a cubic function which was able to fit the data quite well if you follow the pattern, okay? So the green is the original function and the red one is our fit, and still we have some errors, but you got that the model was able to catch the pattern, right? And if you move this way to degree polynomial n, you are able to perfectly fit the data. If you pay attention here, the red curve went through all the points, okay? Now the question is, which one is the most preferable, okay? So that's the job of the regularizer, okay? So we learned about polynomial function, and we learned the context that we have to develop some mechanism that will allow me to answer that, okay, you have to stop at certain point that resemble the function that you are trying to learn. Okay, how do you do that? So to do that, we need to recall our optimization function. So if you recall here, we were trying to learn the theta that minimizes this error function. And here the formulation we use, theta equal to beta 0 and beta 1, and this is the famous linear function that we have talked before, okay? So first we will use a little bit different notation, but the context is quite the same, okay? Because we are using some reference books to read, and that books follows a little bit different notation compared to our previous ones. I'm going to write the same equation, error theta, this guy, with error w, okay? So your theta became w, so that's the difference, okay? and your y is here t n, okay, and your I is n, okay. So this is a different formulation, but the context is the same. This is the error function that we need to minimize to fit a polynomial function. Okay, so if you have got the context, then I'm going to show here in this slide the corresponding models that our algorithm gave as solutions for different polynomials. So here I'm going to show you the 4 version of our models corresponding to each degree of polynomial. Okay, so you can quickly figure out that we are talking about this model with this parameter, this model with these parameters, and this model has 9 parameters which we are showing here. Okay, so if you have got the context, one thing you may have figured this out, that if we drop the sign terms, then the values are actually increasing. Okay, it's 0.19 and then 1.27, then 25.43, and here you have almost in the range of a million. Okay, so if you drop the negative signs, okay, if you have got this context, then we can tell that as we move from a simpler model to a much more complex polynomials, our coefficient values increases over time if we drop the sign term, right? So based on that, we are going to add a new term to our function. Okay, so if you recall, this is the error function, and this is a new term we have added, which we call a regularizer. How it works: this is the error term, and here we have added a term which we are calling it as regularizer. Okay, and it has some very nice properties that you will learn. So if you pay attention, our job is to actually minimize this term, right? That was our objective function here. We want to minimize this theta or w that minimize this term, right? If you conceptualize that we are decreasing in the downwards direction, then this guy will counterbalance, okay? Because remember, we were following in this direction. We were going from a simpler to a more and more complex models. Then someone has to take care of that. Someone has to tell that where to stop. And this guy actually does that, okay? Because if you recall, this one is actually minimizing. So you are going towards 0. And this has the other direction. So this is minimizing and this is actually increasing. Now we may ask that how to control this, what is the sweet spot that actually balances these two, okay? So to do that, we add an lambda parameter for our polynomial regression models, which we call a hyperparameter, okay? Let me summarize. So we want to get to the sine function starting from a simple model with the degree of polynomial is 0. That means the model with only bias, and then we have a linear model, and then we have a model with degree 3. We were still minimizing. So as per the minimization rule, we actually went beyond our expected function, okay? So who actually take me the other way? That's the regularizer, okay? And this term we are calling it as the hyperparameter of the model. So the error term, the regularizer term, and the hyperparameter all together will give you the expected model, okay? So that's the general idea of polynomial regression and regularizer. So few final things to discuss. So this is our polynomial regression with the regularizer that we have been discussing. So sometimes people use a little bit different notation. For example, here they use a additional 2 here because we call this regularizer with a specific name, what we call L2 regularizer. So conceptually, this is the L2 distance where we are adding up the quadratic terms. And in this case, if we are using the L2 regularizer, we are calling this polynomial regression with a specific name, what we call ridge regression. To know, we have other regularizers, for example, L1 regularizer. So here L1 regularizer is adding up the absolute differences, and you are aware of the L1 distance. So this is L1 regularizer, and in this case we are calling the regression as Lasso regression. One final question you may have, that how to choose these lambda parameter values. We use a technique what we call cross validation to choose the value of this lambda, and in our coming classes we will be discussing about this technique more thoroughly. I hope we have understood the concept of regularization. Although we have discussed this in the context of polynomial regression or regression, this is equally applicable to many other models, for example, neural networks. So that was the overall content about regularization, at least at this point. If you have any questions, feel free to ask me at any point. Thank you.